Hello everybody. So I've just made my first video on indefinite integrals. I'm sorry. Look at me. I put this together in a hurry. And I gave it the wrong title, but there it is. I fixed it. Definite integrals. Okay, so I have just made my first video on definite integrals. And now I wanted to do a video where I had some assorted problems. Okay, so I have 3 different problems. All of them are a little bit different. They have different considerations in them. But, you know, I wanted to just give you an assortment to follow up what I showed you in the first video. Okay, so let's do this. Let's start with a quick review of how this is done. Okay, so here is a definite integral. Okay, it has some function in it. Okay, it has a variable, like, so if I see that this is dx, that means that the variable is x. The variable could be different in every problem, but there's some kind of function, some kind of formula right there. And then there's a number here at the bottom of the integral sign. This elongated s is called the integral sign. There's a number there, we call that the lower bound, and then there's a number up here, we call that the upper bound. Okay, so how we evaluate these is we find the antiderivative of this function first, okay? And then we plug in b into that antiderivative. We plug in a into that antiderivative, and we subtract them in the order that you see here. So that's how we'll do it. Now, to do it this way is called the fundamental theorem of calculus, but this is not the only way that you can evaluate a definite integral. It's the only way that we'll be talking about, all right? So you can expect anything that you see to be doable by this method. Okay, with this in mind, let's look at the examples. So here's the first one. We might read this as the definite integral from 4 to 5 for the function 2 over 2x minus 3 squared dx, okay? All right, now, if you think back to that first slide I showed you with how this is done, then I need to find the antiderivative first, okay? Now, the rule for this one, pause for a second. The rule might be different for all of them, for how we find the antiderivative. The formula, the rule may be different for every problem. But for this one at least, then the rule is going to be like this. Okay, here's our rule. It says the antiderivative of u to some power n du is u to the n plus 1 over n plus 1 plus c. Okay, so there's our rule. I need to make this problem fit into this rule by u substitution. Okay, all right, so in a combination of this is the rule that I have in mind and this is the substitution that I'm going to use, here's how it progresses. If I think that this particular integral is going to be workable by this rule, then I would let this thing here, which has that power, be u. Okay, so u is going to be 2x minus 3. That would take care of substituting the x. The dx is substituted differently. I take this equation, which is my substitution, u to x somehow. Taking the derivative of both sides, I get du equals the derivative of 2x minus 3 is 2 dx, okay? And notice that I've got like this part's right here. That's u. In between the 2 times the dx, that's du. Okay, so if I make those substitutions in this next step, it will say u to the minus 2 power du. Now I do have this rule in play. Okay, turns out the power is negative 2. Working it from there, adding 1 to the power, negative 2 plus 1 is negative 1, and I'm going to get this or this. And substituting my original variable x back in, I'll get negative 1 over 2x minus 3 plus c. Okay, so antiderivative's done. There it is. Next part, we evaluate the definite integral with the antiderivative in mind. Okay, all right, so there it is. So look what I did here. I have my original problem. There's my antiderivative. and here are my upper and lower bounds. Okay, and I would put 5 in first. That'll give me negative 1 over 7. And I would subtract, I would put 4 in next. Okay, that would give me negative 1 over 5. Now notice I wrote that there's the subtraction that comes with our rule for doing this, our procedure. And then there's a negative that comes along with the number you get when you put 4 in. So I made sure to put a parentheses there so you see they're both there. There's the subtraction, and then there's the negative number. Okay, doing so amounts to this. I get negative 1 over 7 plus 1 over 5. I add those together. I combine them. I'll get negative 2 over 35. Okay. All right. So there's an example where the technique is u substitution with this rule in mind. I forgot to add there's some fine print for this rule. This rule's only good if that power right there, see that power that we got? This rule's only good if that power is not negative 1. All right. So, okay, now let's contrast this one with another one that looks like this, okay? Now, this is not a u substitution problem, okay? It's not complicated enough to have u substitution. Like for this one, if that was x to the minus 2 power, I wouldn't need u substitution to reduce it down to something simpler. But this here I just do have the variable, so the variable is n this time. I got n to the minus 1 power plus n to the minus 4 power. Okay, so there's nothing more complicated built into that. So I don't need to use u substitution. The rules I need are these two. Okay, so these are some rules I would have given right away when we started learning about how to evaluate indefinite intervals or antiderivatives. Okay, so this one, that's a form of the rule that we just used. X to the n power dx has antiderivative x to the power n plus 1 over n plus 1 plus c. Okay, and then this one, see how this rule is only good if that power is not negative 1? So like right there, that is a negative 1. This rule is not going to be applicable. It'll work for that one. It'll work for n to the power negative 4. It's not going to work for n to the power negative 1. The rule for that is over here. It says the antiderivative 1 over x dx is natural log absolute value of x plus c. 1 over x, if you think about the way negative exponents work, is x to the minus 1 power, okay? So there's our rule that fills in the gap here where this one's no good if the power is negative 1. Do you see why this one's no good if the power is negative 1? What if that power n was negative 1? Well, if I tried to use this rule and I added 1 to that, I'd get 0 and 0, and I'd get some meaningless expression that had a division by 0 in it. Okay, now, so this rule will accommodate that part of it, and this rule will accommodate this part of it. All right, so those are the rules that I need. So I get, like, I look at this first part, 3n to the minus 1. I could see that as 3 over n or 3 times 1 over n. Either way, by this rule here, it's 3 natural log absolute value of n. Okay, then plus n to the minus 4 by this. So I will add 1 and add 1. So I'll get negative 3 and negative 3. Rewriting that a little bit, putting this down there, I'll get negative 1 over 3 into the third power. So there's my antiderivative. Okay. All right, now I evaluate the definite integral with the antiderivative, because that's the whole key to it, and I have that now. So here's my original integral, antiderivative, 1 and 2, okay, and I've put those numbers in. But real quick, notice how when I'm finding the antiderivative, I'm not putting, I have the plus c because I guess it is a part of the antiderivative, but I'm not putting the plus c over here. So what's the deal there? Well, I explained a little bit about that in my first video, but when you do this, when you use the antiderivative and do things in this way to evaluate definite integrals, you you can leave out the plus c, okay? What if you don't leave it out? If you don't leave it out, it will just cancel. It'll be like having a 7 over here and a 7 over there, and what's 7 minus 7? It just goes away. So that's why you can leave it out. But bottom line is you don't have to worry about it. Okay, so let's see. Now I gotta take this antiderivative. I gotta put the 2 in first, and if I do that, I'll get this. Okay, then I got my subtraction, and then I've got to put the 1 in next. Okay, and if I do that, I'll get this. All right, now notice how I've got my parentheses there in red to block this off, because that subtraction has to apply to everything that comes after it. So I just write that to be careful. If you were going to plug this into a calculator, you would need to use a parentheses to say that that subtraction applied to all that stuff, okay? So I put it in there like this, just so that it's clear that you would do that. So here's what I got when I put in 2, there's my subtraction, and here's what I get when I put in 1, all right? Now, as I didn't use a calculator and I just broke this down, this is what I got. This part was 0. I subtract negative 1/3, that's 1/3. Okay, and those are all the numbers, you know. Then from there, I put it in a calculator, and I get 2.3711. On MyMathLab, some of the questions might say to round your answer to so many decimal places. Say this one says round to 4 decimal places, and that's what I got, rounding to 4 decimal places, okay? But just be careful with that subtraction. Know that however big this is, when you plug in that lower bound, that subtraction applies to everything that you get, okay? You probably will just put this step right here in the calculator. And if you do, put it in like that just to be safe about it, all right? Sure, if you left that parentheses out, your calculator wouldn't distribute the subtraction the way that it's supposed to be done. Okay, let's try one more. So here goes. This one is the definite integral from 0 to 3 for this. Whoops, I forgot something. Dx, right? Okay, so the dx indicates that x is the variable, and then, in fact, in that formula, the x is the variable, okay? All right, so why do we have the dx? Well, in case we use u substitution, it's part of all the bookkeeping we have to do to substitute the variable out. All right, we do need u substitution in this problem. So I get that, and again, my first step is to find the antiderivative, and this one is complex enough that no basic rule applies to it. By basic rules, I mean like these are basic rules. X to a power, 1 over x, you know, there's nothing more complicated than just the x, okay? And here, there obviously is way more stuff, more complicated than those basic rules apply. So what I was thinking when I saw this is that the rule would be 1 over u du, okay? Because I've got this thing down there. And I noticed that if I took the derivative of it, I almost get that thing up there. So I think if that thing on the bottom could be the u, and the thing on the top will end up being the du. That's what my impression was when I saw it, all right? Anyway, so I think that'll be my rule, which says that the answer is natural log absolute value of u plus c. So this is the rule that I think will be applicable for this, okay? And I don't know until I go through and put everything into it. So if I think this is the rule that applies, that bottom part is u, x squared minus 6x plus 10. That would make the du, what's the derivative of x squared minus 6x plus 10? That would be 2x minus 6 dx. Now, the objective is to substitute the u and the du in there without anything left over. We want to change the problem from being in the variable x to being in the variable u so that this rule, or whatever rule is appropriate, works. So that says x minus 3 dx. It doesn't say 2x minus 6 dx. So they don't match. And if they don't match, I can't substitute them. So I need to think if I can manipulate this equation in some way So this does fit up there, and it can be substituted. And what I notice about it is that if I take this equation, and it is an equation, you see the equal sign, so you can do to it whatever you can do to an equation, such as multiply both sides by a half, or divide both sides by 2, same thing. What happens if you get 2x minus 6 all divide by 2? You get x minus 3, and that's what we see right there, okay? All right, so doing that is what makes things fit. So I can see like this part right here, that's the du, and we'll get successful substitution of that, du over 2 actually, and then this part right here underneath it is the u, and then everything can be substituted, and that's the ultimate objection of doing an antiderivative by u substitution. So I do that right in this step, and I'll get 1 over u, and x minus 3 dx, which you see there is du over 2 like that. That du over 2, well, the over 2 is a factor of 1/2, 1 over 2, which I factor out. Our answer to the antiderivative 1 over u du is natural log absolute value of u plus c, which you see right here. Putting u back in terms of x, u is x squared minus 6x plus 10. So there's my antiderivative. Okay, so I got that. And from here, you know what happens. We plug the numbers in. Here's our problem. Here's our antiderivative. If I put 3 into the top, I'll get 1. Then I subtract. If I put 0 into the top, I'll get half natural log 10. Okay, now this one, that's not very complicated. It's this number minus this one, which we would do in a calculator, okay? Especially because this one says round to 3 decimal places. Need a calculator to do that. So if I do that, I got negative 1.151, rounding to 3 decimal places. Okay, so let's leave it with this, that in general, like the technique for evaluating a definite integral is not that difficult. So we do like this, right? We find the antiderivative, we plug in the upper bound and the lower bound. The only variation that I think could come from this, from one problem to the next, is how you find that antiderivative. Some of them may be more complicated than others. Some may take u substitution. Some may not, right? But you have to take it on a case-by-case basis. Nonetheless, some technique you learned for antiderivatives already somewhere will be applicable. You'll just have to figure out which one it is.